So hello again, everyone. Let's start by stating what is our problem. So we have a lot of systems now that do not run only on a single computer, but have the distributed component. Actually, most of the programs that you use today, including the browser, depend on network and computation as well, right? Because it's, for example, important that you decrypt your connection packets. At the same time, it is important what is the delay on the network. In order to model such a system, we need to take care of these components. So network latency, network bandwidth, computation costs like cryptographic signature checking or data structure lookup in the hash tables. In order to simplify the problem somewhat, we assume that we have capacity insensitive networks. So for example, if I use 100 megabit link, but I only use, say, 1 megabit or 100 kilobytes of the download or upload, like during this presentation, that's sufficient to just consider latency. With the computation, we will model it as a time to completion, right? So we will basically wonder how long does it take for computation to finish, and assume that the computation can be modeled as basically constant or this latency distribution or constant cost. So that means that everything for us will be latency. That's somewhat a simplifying approach, but with increasing number of applications is actually very close to being true. So the plan of this presentation is that I told you why we want to use latency distributions as a general model for distributed systems for both computational and networking components. Then we say how to implement very simple latency distributions. We tell how to manage the sequential compositions. So for example, I send you the packet and then you send me packet back, or I send you the packet, then you decrypt it, and then you send the packet back, and I also decrypt it, right? So this is sequence of events, and it can be basically modeled as sequential composition of the distributions to get a distribution of latencies for the whole process. So that's basic interaction. Then we will talk about interactions that require parallel composition. We have two main parallel compositions that we care about that we will use to build more complex behaviors from. First is first to finished, and the second is last to finish. It's like conjunction and alternative in Boolean logic. Then we will go on how to model the network, so like network broadcast, for example. And we will give the example of time service and DynamoDB consensus. So why DynamoDB is so fast, for example, right? We can model basically the time it takes DynamoDB to update after each new tuple is inserted to database, and how long does it take to read, depending on the configuration of DynamoDB. So first, let's talk about distributions. So we have the distribution, basically, of probability of arriving packet at a given delay, right? So this is distribution, say, we model only some threshold, up to some thresholds. If it goes longer than six seconds or 60 seconds, depending on the scale that you want to model it, you will drop the packet anyway, right? The operating system has the maximum threshold of how much time it accepts the packet to live on the network, and if it arrives too late, it is just dropped For the application, it doesn't matter. So everything that goes beyond certain threshold, in this case 6, is considered something that never arrives. So it's like lost forever. And this is important distinction because that means that we need improper distributions. So distributions that allow some number of packets to be lost. Otherwise, they behave very much like probability distribution functions. However, sometimes certain things can be better explained on cumulative distribution functions, which basically means that at each point, the function has the value that corresponds to likelihood that packet arrives by certain time. So maybe it arrives at moment with delay up to 5 with 80% probability, right? And this CDF is improper CDF because it also doesn't grow up to 1. So you never have a certainty that packet arrives because it can be simply lost. So this is the representation of the same function as above. So the first representation is PDF, the other is CDF. And this is basic probability, so I will not bore you with it, but it's important to see that it can be equally simply described in Haskell. So since we have a distribution over finite interval, over small interval, and we discretize it into discrete points, we can basically say that we have a series and then implement it as a list of values, right? And the lost packets will not be given a number. It will be just leftover from total probability of 1 and sum of everything that is in PDF in the list, right? And to work with cumulative distribution functions, we need to convert them from PDFs to CDFs and back again. So we have a finite integration operator here. For discrete case, it's really simple. It's just scanl that adds from 0 and drops the first number because the first number will be always 0. Right, and then we have a backward difference operator that is inverse. So we can easily test this with quick check, and this is approach that we use all over this presentation. So you can look at the PDF of the paper, and you will see literate Haskell code that has been tested with quick check. We didn't prove correctness, right? It's much faster to prototype with quick check and to check the laws in quick check. If it's exhaustive enough, you will have satisfactory compliance with your mathematical expectations. So now, basically, to compute a CDF of any latency distribution object data type, we just compute cumulative sum of PDF. And the same, you can construct the latency distribution from CDF by basically using differential encoding or finite difference operator. Now, we have special values here among the latency distribution, special values because they will be at t, right? So it's basically a series that starts with 0 and then has 1 at the end. And since we basically cut the series after it starts being all 0, we have a finite list that we can easily compute with. The same is for preservation or attenuation, right? So we may just lose the packets. We basically divide the packets into, say, 80% that are preserved, that are forwarded with no delay, and 20% that are immediately lost. And then we implement the basic operations. So sequential composition, as I said before, is basically a composition of distributions of two events that were basically invoked in sequence. So the second event can only start as soon as the first event has finished, right? And the nice properties we have there, it's associative, it's basically monoid. It's commutative monoid, actually. It has neutral element, so mempty is basically no delay, right? So if we do something and then we do something else that gives us no delay, that's the same distribution like if we did only the first thing in the first place. And the null element, which is all lost, right? So if we first need to prepare coffee and then we do something that means that we will leave our house and never return again, then we never come back home, right? So if there is a situation where we could require completion of events that is basically always losing all the packets, then we just have the same distribution as we lost all the packets in the first place. And it is relatively easy to implement because you basically take PDFs of two probability distributions and compute convolution of this. And the convolution, for this, I would refer you to Doug McIlroy excellent functional power series that just gives us the definition of convolution as very short functional recursive program. Now, if we want to consider the situation when we either communicate one way or the other. So for example, we will consider the task completed if we first send it to one partner or we'll send it to the other partner because we don't care. It's like we have two banks that can do some operation on our behalf, right? Or two co-workers. So if we say reach Anne with a phone call, and she realizes our task that we cannot do ourselves because maybe our computer crashed, then the fact that Barbara also wanted to help us but was not available on the phone doesn't matter, right? So, and the same, if it turns out that we try to call Anne and Barbara and Anne is unavailable, then basically Barbara will complete these tasks. So this is again associative, commutative, and the neutral element of this is the null element of the previous operation, right? So basically, if we have something that loses all the packets, then we just ignore it here. It's neutral. It doesn't change anything. At the same time, if we have the distribution that always returns with no delay and always guarantees success in no time, like I wish I had a way to do some things this way, then it doesn't matter that you know, if you say have Anne next to you and you can ask Anne to help you and she will do it in such a fast way that you will not even notice, right? Then it doesn't matter that Barbara is unavailable or is she available, but she doesn't have time this hour. She needs to wait hour until she will be able to do anything, right? So that's the null element here. Interesting part is that it's also monotechnically increasing by some measures. So you can use it when checking for convergence, that there is guaranteed convergence if the parallel alternative is involved. But I will not introduce the metrics because of shortness of time here. So I will refer to monotonic property and the metrics to the paper. And we have a conjunction. So we want maybe to realize some task that requires cooperation from both Anne and Barbara, right? So we call Anne and call Barbara. And, it's important task. It's something that they need to both be involved with, like assuring that everybody in the team, if we have 3-person team, us, Anne and Barbara, that everybody in the team is informed that tomorrow we work at home, right? Because the office has burned, for example. Then we need to call them and successfully call both of them. And we consider this task realized when both of them are informed. And it, again, is associative. It is also commutative because it doesn't matter in which order we call them. But the neutral element here is, this is actually null element here. Null element is all lost, and the neutral element would be 1Q, right? So that everything succeeds immediately. And it is also monotonically increasing. What is nice about it is that we can also compute this easily in Haskell using the from CDF and CDF function that we defined before. We basically compute the convolution, but on CDFs, right? We just need to extend the series first so that there are zeros appended so that they are both the same length. And similar implementation is also feasible for first to finish. So what we see here is this very simple algebra where we have special elements that are either null elements of one operation or the other, a neutral element of one operation or the other. And we have this first to finish and last to finish and after operations. And depending on what we want to talk about, we can basically use these operations. The simplest example is basically, instead of latency distributions, we can just estimate what is the latest possible arrival. So if we lose any packet, the latest means never, right? But maybe our processing will always guarantee that ultimately it arrives. And then we have an alternative implementation of this algebra. Once we have this algebra on latency distributions, we may want to model an entire network. And it's easier to do it by basically using upper dark triangular matrix of latency distributions. Notice that this is not a matrix of linear algebra because our operations do not have inverse. But we can use linear combinations of any of these operations because of distributivity, basically, which is not always preserved, but we can still keep the addition and multiplication of different kinds. So we will define our matrix multiplication where plus and multiplication, so addition and multiplication, are replaced by first to finish or and after or sequential composition. And that means that we basically will have matrix multiplication that corresponds to the situation where we have basically situation where we broadcasted the message to all members of the network using the gossip algorithm. So everybody who got the message will broadcast it again. We try to broadcast it again to every other node. Right, and we can easily check how long it approximately takes us to broadcast the thing to all nodes in the network by making a consecutive approximation. Basically, we're multiplying the matrix of network connections or network connection latencies by itself n times, which basically means in n hops, right? We reach the target. And basically, because of the monotonicity properties that we mentioned before, we will ultimately converge to latency distribution here. So basically, initial terms of the series will be computed consecutively until we get the result. Now, that is basically a time service or broadcasting to every node in the network. Another interesting network service would be DynamoDB. So in DynamoDB, we have n nodes that hold database. And there is configuration parameter k. So whenever you write a tuple, then you need to send the tuple to k nodes and get confirmation from them successfully. If you get this confirmation, it was written successfully. So we need k nodes out of n to confirm it. For simplicity, we send the write request in our test to all n nodes to guarantee that we get the answer as soon as possible. And then the guarantee is that if we perform the same thing for the read for n minus k plus 1 nodes, then we know that and we get the same answer, right? Then we know that there is read consensus. So you cannot possibly have written the tuple to k nodes and read a different tuple from n minus k plus 1 nodes, right? That means basically that you get the credible answer. And that makes for a very, very fast database algorithm, right? Because you can basically distribute the database to many nodes. You can send them write requests or read requests. And if you get only k answers for a write request or n minus k plus 1 answers from read requests, you succeed. So if you have a read intensive database, then you say that read consensus will be 1 node, and write consensus will be the positive answer from all nodes, so basically n. That makes the database configuration that answers very quickly to read requests because any node can answer it, and allows for rare and relatively long write requests. And I can refer you for details to a DynamoDB paper. But it generally is one of production databases that many of cloud services use. So to do that, we need to look at the exclusive sum of the latencies and latency distribution. So basically, just like for probabilities, we can sum the probabilities of exclusive events. The same way we can sum the distributions of exclusive events. So that's what we use the exclusive sum symbol here. Additionally, we use convolution and 2-element series, that is the complement and the second term. And this is basically the recursive equation that allows us to basically compute the latency of DynamoDB. And for a small number of nodes, like probably your DynamoDB database has, I don't know, maybe for a small company, just 5 nodes. For a large company, maybe even 100, but you can still compute the terms here. So you can compute how long it takes for DynamoDB to respond for a given network latency, right? And the computational latency, which is great. And the implementation in Haskell is not much harder, right? So it's really simple to audit computation. You can have like a formal model of your network latency that is auditable and explainable to people. So again, if we have this simpler approximation of everything as a latency distribution, we can model distributed system performance successfully. It's easy to implement in Haskell. And we can actually look and verify deep insights about latency distributions using just quick check. Just say that, check that it most of the time it's good, right? By quick check, by random sampling of latency distributions. Next step would be to prove it in Coq, but I'm afraid this task still awaits funding. So if you are interested, I can also help you with that. I don't think at the moment I would do it by proving. And that's also an observation that deep math is sometimes easier to grok and write about if you think about it as a program. Also, compiler can check you. Do you have any questions?
One quick question. Thank you for the presentation, but we are running out of the time actually. If you did some measurements in terms of latency, do you have some benchmarks? Just curiosity, and quick question, quick answer.
So I have expressed certain systems of up to 20 or 100 nodes and checked that the computation at a certain granularity level of saying dividing the series to 100, limiting it to 100 terms. So 100 terms means that you think about like 10 milliseconds latency and the limit of 1 second, right, for computation for the answer. For this kind of systems, you get the answer basically within a few seconds, right, or using Haskell. And you get the answer actually for multiple variants of the problem, because we are mostly interested not in a single answer. That would be very, very quick to answer. But mostly we are interested in questions like, for any network topology, for random network topology, is it likely that something breaks or something will have latency greater than 1 second, right?